and welcome to my presentation on comprehensive Twitter sentiment analysis using machine learning. I am Srijita Shah from Ivy Professional School. Today I will explore how machine learning can be used to classify social media, text data, and extract valuable insights from Twitter. This project represents a complete end to end solution for understanding public opinions through automated sentiment analysis. The significance of this work lies in its practical applications for brand monitoring, customer service optimization, and market research in today's digital landscape. Let me walk you through the comprehensive agenda for today's presentation. I have 20 structured sections covering all the aspects of the sentiment analysis project, beginning with the introduction and project overview, then deep dive into the dataset description and the challenges I have encountered. Next, I will explore the sentiment distribution patterns and entity analysis using TF-IDF vectorization, model selection strategies, and performance comprehension. So, what is sentiment analysis? Sentiment analysis is the automated computational process for identifying and categorizing opinions expressed in text data, determining whether the sentiment is positive, negative, neutral, or irrelevant. Twitter serves as the primary data source because it provides real time vast amount of public opinions on countless topics, making it invaluable for understanding public perception. The main project goal is ambitious yet achievable, building a robust classifier that accurately categorizes tweets into four distinct sentiment categories. The business applications are extensive and highly valuable, from brand monitoring and reputation management to customer service optimization and comprehensive market research. So, my dataset comprises of two substantial CSV files, Twitter training CSV containing 74,682 total records, and the Twitter validation file having 1,000 records. And then the structure includes four essential features: tweet ID for unique identification, entity representing the brand or the topic discussed, sentiment as the target variable, and content containing the raw tweet text. So the target classes consist of four sentiment categories: positive, negative, neutral, and irrelevant, providing comprehensive sentiment coverage. The dataset focuses on primarily on the gaming companies, tech giants, and the social media platforms, ensuring domain relevance and practical applicability. These sentiment patterns is specific to the technology and gaming industries while maintaining generalizability. In the slide, the data quality assessment revealed several critical challenges that required immediate attention: missing values, so that affected 686 tweets lacking content, representing 0.9% of my dataset is a manageable, but it is significant issue requiring careful handling. So I identified 3,280 18 duplicate rows constituting 4.3% of the data, which could skew the model's performance if not addressed. The text data exhibited typical social media noise, including URLs, hashtags, mentions, and excessive punctuations, numbers, and colloquial language that needed systematic cleaning. Class distribution analysis revealed slight imbalances between sentiment categories, which could impact model training effectiveness. After comprehensive pre-processing and cleaning procedures, my final dataset contained 70,387 high quality tweets, ensuring robust model training and reliable performance evaluation. The sentiment analysis the distribution reveals fascinating insights into public opinion patterns. Negative sentiment dominates with 22,808, that is 30.1% of the data. Positive sentiments having 21,109, 27.9%, that is the second highest. Neutral is having 18,603, that is 24.6% of the data. And some of are irrelevant, that is 13,162. This distribution is remarkably balanced for real world social media data with only a slight skew towards negative opinion. This pattern aligns with the psychological research showing that the people are more motivated to share their negative experience, making this distribution typical and valuable for training robust sentiment analysis models. From the entity analysis, it reveals that comprehensive coverage across 32 unique entities with remarkably balanced representation. The top include Tom Clancy's Rainbow Six with 2,435 tweets, League of Legends with 2,431 tweets, Madden NFL with 2,429 tweets, Microsoft with 2,428 tweets, and Call of Duty with 2,425 tweets. This balanced distribution is crucial for preventing model bias towards specific brands of topics. The domain focus is heavily concentrated on video games and technology companies, reflective the digital native audience of Twitter and their engagement with gaming and tech content. The balanced representation prevents any single entity from dominating the learning models or the process, resulting in more generalized and robust sentiment classification level. In the entity versus sentiment cross analysis slide, I have seen that there is a cross analysis between the entities and sentiment that reveals compelling patterns in brand perception and community engagement. Each brand or game demonstrates a unique sentiment profile reflecting distinct community dynamics and user experiences. League of Legends and Microsoft exhibit relatively higher proportions of neutral and positive tweets, suggesting stronger community satisfaction and engagement. Conversely, Call of Duty and Madden NFL received a higher volume of negative mentions, potentially indicating ongoing issues with the game mechanics, updates, or the community management. These variations highlight the importance of brand specific sentiment monitoring and the need for tailored response strategies. Understanding these entity specific patterns enables businesses to benchmark their performance against competitors and identify areas for improvement in community engagement and product development. Here, the text length analysis provides crucial insights into Twitter communication patterns and content quality indicators. The mean tweet length of 109 characters with a median of 91 characters demonstrates the concise nature of Twitter communication, staying well within the platform's constraints. The range spans from 1 to 957 characters, showing diverse expression styles from brief reactions and detailed opinions. The standard deviation of 79.6 shows and indicates moderate variability in tweet lengths. Most tweets are appropriately concise, reflecting Twitter's format and user behavior patterns. Shorter tweets might contain more concentrated emotional language, while longer tweets may provide more context but potentially dilute sentiment signals. Sophisticated four-step Preprocessing pipeline ensures optimal data quality for machine learning. Step 1 involves basic cleaning, including lowercasing for consistency, URL removal to eliminate the noise, and mention or hashtags. Step 2 implements text normalization. Step 3 includes advanced preprocessing with NLTK tokenization for proper word boundary identification and English stopword removal. Step 4 applies wordnet lemmatization, reducing the words to their base forms for semantic consistency. Each step serves as a specific purpose in transforming chaotic social media text into clean, standardized, processed content ready for feature extraction and model training, significantly improves the classification accuracy. The word frequency analysis reveals distinct lexical patterns across sentiment categories, providing valuable insights into language use and sentiment expression. Positive sentiment features words like game having 3080 occurrences, love, good, like, and really, indicating appreciation and enjoyment. Negative sentiment shows like game, get, like, shit, and fix, reflecting frustration and dissatisfaction. Neutral sentiment includes Johnson, Game, Amazon, Gate, suggesting informational content. Irrelevant sentiment contains player, game, see. These are the analyses that are fundamental for understanding sentiment specific vocabulary and helps identifying the discriminative features for classification. So, the word cloud visualizations serve as multiple critical purposes in the sentiment analysis pipeline. It provides intuitive visual representation of sentiment analysis, helping identifying the distinguishing between sentiment categories. Through pattern discovery, I observe a clear positive and negative lexicons emerging. Words like love and good clustered in positive environment or sentiment, while did dominate negative sentiment visualizations. This feature validation confirms that gaming terms and emotional expressions create distinguishable sentiment specific word clusters, validating the preprocessing decisions. These visual insights directly guide the feature engineering process, helping to select the most informative words and engrams for model training. The word cloud serves as both explanatory analysis tool and communication aids, making complex textual patterns accessible to the stakeholders. Feature engineering extends beyond basic text preprocessing and to capture nuanced communication patterns in tweets. I've created 6 numeric features that provides additional context for sentiment classification. Word count averages 10.4 with a standard deviation of 7.2 indicating typical tweet verbosity. Character count means 70.5 with 49.8 standard deviation complementing the earlier length analysis. Average word length of 5.95 and standard deviation of 4.16 captures vocabulary complexity. Exclamation count averaging 0.38 having the standard deviation of 2.72 indicates emotional intensity crucial for sentiment detection. Question count of 0.18 and the standard deviation of 1.94 captures inquiry patterns. Uppercase counting average of 7.83 having standard deviation of 12.0 reflects emphasis and potential shouting behavior. These are the features that are significant because they capture communication style elements that pure text analysis might miss. Term frequency inverse document frequency. Vectorization transforms our preprocessed text into numerical features suitable for machine learning algorithms. The configuration includes 5,000 maximum features, balancing computational efficiency with information retention. The n-gram range of 1,2 captures both individual words and two-word phrases, enabling the model to understand context and phrase level sentiment indicators. English stop words are excluded to focus on meaningful content words. Our data split follows the 80-20 rule with 56,309 training samples and 14,078 testing samples, ensuring robust model evaluation. Label encoding converts the string sentiments to numeric values 0 to 3 for algorithm compatibility. The final feature matrix contains 56,309 training samples across 5,000 features, creating a comprehensive representation of the text data. This is crucial because it weights words by their importance across the corpus, reducing the impact of common words while highlighting the distinctive terms that better discriminate between the sentiment classes. The systematic model selection strategy evaluated three distinct algorithms to identify the optimal approach for sentiment analysis classification. Logistic regression achieved 68.51% accuracy, representing a solid baseline with good interpretability but limited performance on complex text patterns. Knife bias reached 63.88% accuracy, demonstrating the challenges of independence assumptions in text data where word relationships matter significantly. Random forest emerged as the champion with 87.09% of accuracy, leveraging ensemble learning to capture complex patterns and interactions in text features. We employed five-fold cross validation with stratified sampling to ensure robust performance evaluation and prevent overfitting. The stratified sampling maintains class distribution across folds, crucial for imbalanced datasets. Random forest superior performance stems from its ability to handle high dimensional text data, capture high dimensional feature interactions, and averaging. The performance comparison clearly demonstrates the random forest superiority across all the evaluation metrics. Logistic regression achieved 68.51% accuracy with a 67.32% cross validation score, showing reasonable but limited performance for this complex but classification task. Same goes for knife bass, but random forest dominated with 87.09% of accuracy and 85.03% of cross validation score, representing a substantial improvement over traditional approaches. Random forest shows and delivers exceptional performance across all evaluation metrics and sentiment classes. Therefore, this is chosen as the best model. The confusion matrix provides detailed insights into the model's classification patterns and remaining challenges. The model excels at predicting negative sentiment with 3,856 out of 4,261 correct predictions, achieving 90.5% of accuracy for this crucial business category. The main confusion occurs between the semantically similar classes, particularly neutral and positive sentiments, which is understandable given their subtle linguistic differences. A notable challenge area involves 231 irrelevant tweets misclassified as positives, suggesting some promotional content can include the features like positive language patterns. Feature importance analysis reveals the key sentiment indicators. Positive features include love, excited, fun, while negative indicators encompass fix, trash, bullshit. These insights are valuable for businesses understanding what language patterns drive sentiment classification. The practical application of the sentiment analysis model span multiple critical business functions with significant strategic value. Brand monitoring capabilities enable organizations to track real-time public perception shifts, identifying emerging trends and potential reputation issues before they escalate. Customer service optimization include identifying and prioritizing the negative feedback for immediate response, improving customer satisfaction and retention. These are the summary and key achievements of my project. The key technical contributions include advanced text preprocessing techniques, comprehensive feature engineering incorporating both textual and numerical features, and systematic model comparison ensures optimal algorithm selection. The balanced performance across all the sentiment classes demonstrates robust generalization capabilities suitable for diverse business applications. This work bridges the gap between the academic research and the practical business implementation, providing a complete framework for social media sentiment analysis. This methodology and insights presented today can be directly applied to various industries and use cases, making this project a valuable contribution to the field of social media analytics and business analytics environment or business intelligence. So, thank you so much for watching this video.